Vegetation, in endless varieties of shape, size and colour, mantles the earth. Among its many properties, it all contains oil. Whilst some plants bear only minute traces, others, particularly some seeds, nuts and other fruits, contain a great deal. And just as the juice may be squeezed from an orange, so we may crush oil from the fruits of these oil-rich varieties known as oilseeds. This oil, vegetable oil, is in great demand, not only for food, but for use in industry. And in consequence, a vast international trade has grown up around oilseeds. Sources of commercial oilseeds are widespread throughout the world. Within the hot tropical belt, conditions favour the production of many varieties, a piece of economic good fortune for these regions. One type grown throughout the whole of this tropical belt is the groundnut, or peanut. The seed of a small plant of the bean family, it is cultivated on a vast scale and is regarded as one of the most important oilseeds. In complete contrast to the tiny groundnut are the palms. One, the coconut palm, towers nearly 90 feet high when matured and bears about 50 of the familiar nuts at each crop. When these nuts are split, the inner white flesh is sun-dried and becomes copra, about 66% oil. The other palm, the oil palm, bears oilseed not in large single nuts but in clusters or heads of up to 2,000 smaller ones called palm fruit. Palm fruit yield two different oils: palm oil from the outer husk or pericarp, and palm kernel oil from the hard inner nut. The cotton plant, after the cotton fibre has been stripped off, yields an additional harvest of oil from its seed, cottonseed. And there are many others, by no means all of which grow in the tropics. The soya bean, rapeseed, a kind of mustard, sesame, the sunflower seed. These and many more play an important part in providing vegetable oil for food and industry. And in addition, the residue of most oil seeds, with notable exceptions such as the castor bean, are a valuable source of protein and are much used for cattle food. Let us examine a typical oil seed and see how the oil is contained and the methods of extracting it. Under a microscope, the tissues are seen to consist of thousands of tiny cells linked together. Within the retaining cell walls, the oil content lies, tiny globules of fatty oil. It is these globules which have to be extracted. There are two ways to do this. The first method, squeezing it out, remember, is called expulsion. But as the cell walls are tough and resilient, expulsion is more effectively carried out if the seed is first broken into fragments, then heated. Pressure will now fracture the walls more easily and squeeze out or expel the oil. Commercial oil mills, handling many thousands of tons each week, apply exactly the same principle on a much larger scale. For the initial fragmenting of the seed, cracker rollers are used. In general, these consist of a number of heavy serrated rollers rotating in opposite directions. The seed is fed between them, and is crushed to fragments by the immense weight. The heating takes place in vessels known as kettles. These are containers which are divided horizontally into several compartments. The fragmented seed fed into the top is heated by steam which passes through the walls and floors of each compartment. Stirred by gently rotating blades, the seed gravitates through outlets in the bottom of each section and emerges steaming hot from the last section to drop straight into the expeller. The expeller contains a hardened steel barrel laced with fine slots. Inside it, a screw rotates and crushes the hot seed mass against the walls of the barrel, squeezing out the oil through the slots. But the extruded seed mass which emerges still contains a certain amount of oil, for however much pressure is applied, not all the tiny globules can be expelled from the cell structure in this way. Some are inevitably trapped. Whilst some seed residue still containing oil is used for cattle food, in other cases, where it is commercially necessary to extract more of the oil, a second method of extraction called solvent extraction is applied. Oil is soluble in a spirit. So if the extruded seed is washed in a high-grade spirit solvent, the remaining oil globules will be dissolved and absorbed into the spirit. In commercial practice, an economic method of solvent application known as countercurrent is applied. Countercurrent involves the use of a cycle of 5 solvent tanks and works in this way. Spirit solvent flows through the 5 tanks in one direction, whilst batches of seed pass through in the other. In tank 5 is seed fresh from the expeller with a high oil content. In tank 4, the seed has received 1 previous solvent wash. In tank 3, it has had 2 washes. In tank 2, 3 washes. And in tank 1, it has had 4 previous solvent applications and consequently bears only the last traces of oil. Completely fresh solvent is applied to the seed in tank 1 and readily dissolves and absorbs the remaining obstinate oil traces. This solvent is then passed to tank 2, which contains less washed seed, slightly richer in oil. It absorbs a quota from this and is passed in turn through the remaining tanks of the cycle. The seed in tank 1, having received its 5th and last solvent application, is removed from the cycle, and its place is taken by the seed in tank 2. This in turn is replaced by that in tank 3, and so on until a fresh batch is introduced into tank 5. The overall effect is a semi-continuous flow of solvent increasing in oil saturation in one direction, and a similar flow of batches of seed progressively reducing in oil content in the other. Hence the name countercurrent. The fully saturated solvent, on leaving its 5th tank, is separated from the oil by distillation, which vaporizes the spirit and leaves behind the non-volatile oil. Having extracted our oil by either or both methods, let us examine it. It is at this stage crude oil, dark in color and with a noticeable smell and taste. So before it is suitable for use in food products, it must undergo refining. To understand the refining processes, we must first examine the chemical composition of the oil. Vegetable oils are triglycerides. That is to say, each molecule is composed of a glycerol or glycerine framework linked to 3 fatty acid groups. These fatty acids may be all of the same type, or they may be mixed, as in so-called mixed triglycerides. The predominance of a given type determines certain characteristics in the resulting oil. But there are also other substances present, including enzymes. These enzymes are a natural catalyst which cause some liberation of the fatty acids from their glycerol units. The presence of these liberated or free fatty acids causes the objectionable taste and smell of the crude oil. So, to remove them, we employ an alkali which neutralizes these free acids. Alkali is introduced into the crude oil, and the alkali molecules combine with the free fatty acids and create a thick, soapy curd. This curd is soluble in hot water and may be easily dissolved out. The quantity of alkali used is, however, highly critical and must be calculated by a test, titration. A measured sample of the crude oil, mixed with a color reagent, has alkali carefully added until the reagent color indicates that all the free fatty acids have been neutralized. A simple calculation then shows how much is required to neutralize the whole batch. In the refinery, the neutralizing takes place in totally enclosed containers. The oil, sealed into them and constantly stirred by rotating paddles, is heated by steam coils inside the tank. By duplicating the container on a small scale, we may see how this process takes place. The alkali is sprayed in, the curd forms, and hot fresh water is then pumped in, dissolves the curd out, and settles with it at the bottom of the tank. This curd may then be drained off. In the refinery, a small eye port at the bottom of the tank shows by the change of color when all the curd has been removed. The oil left behind contains no free fatty acids. But there still remain the other factors, the color and the slight smell to be dealt with. Fuller's earth, sucked in by vacuum, is used to decolorize the oil. Again, in a glass vessel, we see that the fine particles of earth absorb the coloring matter in the oil. A filter will then retain the color-soaked particles and pass only the clear oil. Pressure filters are used in the refinery. Now the oil is ready for the last stage in its refinement, which takes place in a container where steam is bubbled through it under vacuum for some hours to remove the volatile elements responsible for any remaining smells and tastes. And the oil is finished. Pale, tasteless, with no smell, it has come a long way from the raw oilseed. But the refined oil stage is only half the story. The rest lies with those who use it. Margarine manufacturers take a large proportion of all the finest vegetable oil processed, and oils refined to varying standards are used in many other ways. And finally, soap, one of the most important of the many products dependent on the world's supply of oil-bearing nuts, fruits, and seeds.